Thank you for the kind introduction and inviting me for this talk. And good evening to all the participants and all the august audience over here digitally. Definitely, yes, as rightly mentioned earlier in the introduction as well. So today I'm going to talk about on complex eigenvalues, especially, and I have given the title of the talk as Complex is Easy Again, Complex Eigenvalues and Their Intuitive Meaning with applications in science. So I'll start this whole discussion to make it relatively more interactive, although I'm not available here physically because of the physical boundaries, definitely we all are aware of. But I will take this opportunity to make it as much as interactive as possible and definitely look forward for your responses on my LinkedIn and definitely through the organizers. But to begin with, I'll start with a small anecdote why I chose this topic. Definitely, eigenvalues in Journal Applied Mathematics and Mathematical Modeling, which is the theme of this particular, I would say, digital conference or confluence, is mathematical multidisciplinary application and design. So during my PhD days, I mean, it was a question which one of my friends asked me that, do you know what is the physical significance or a geometrical meaning of an eigenvalue, and in particular complex eigenvalues? And we used to deal with eigenvalues a lot, but to actually get into the intricacies, to make it like offhand, solution, and to tell somebody that what is eigenvalue and geometrical interpretation of that, especially in the complex domain, is what actually always excited me thereon. So that's why I chose this topic. With no further ado, let me get into that. As I promised, to make it more interactive, so I'll share a few questions. The answers of that will be there during the presentation, partly. And I look forward for the answers so that to make it more interactive earlier, many of you, or maybe all of you, if you like, who would like to interact with me can later on pass on the answers and their understanding through the LinkedIn page of mine. So the first question is, can you tell the famous algorithm that utilizes eigenvectors and has revolutionized the World Wide Web? Yep. Second is, can you guess the worth? Yes, I underline this. The worth of eigenvectors in the year 2004 for Google. Yep. So please stay tuned and be inquisitive about the answers hidden in the presentation. Let me start formally the presentation with an agenda. So to begin with, I'll talk about the why we should learn, and we have to learn eigenvalues and eigenvectors. And I'll try to appreciate all the audience here by motivating you enough by the applications in science, in applied mathematics, and in all the STEM, right? Science, technology, engineering, and mathematics, and definitely biology as well. So second part of the presentation is about, I'll go into the depths of basics of eigenvalues, eigenvectors, especially complex eigenvalues and its mathematical modelings and application of complex eigenvalues. Third, I will enter into the applications of real and complex eigenvalues in science, especially in aerospace, broadly mechanical sciences, applied mathematics, broadly mathematical sciences, and yes, definitely data science. Then I'll touch upon the stability and phase portraits for especially for PhD and postdoctorate students and faculty who are interested in nonlinear dynamics and chaos, which is one of my favorite subjects. And I'll end the presentation with live demonstrations, which I would like to start and collaborating with a couple of institutions like AMS and MAA on the field of visual mathematics by demonstrations of complex eigenvalues using Mathematica. All right, so to begin with, as I promised, so this slide is dedicated towards that why should I learn eigenvalues and are they really important? Yes, so let me start by addressing again and raising two questions. So I'm asking again, can eigenvalues crash an airplane? Can eigenvalues collapse a bridge? These are very fascinating, interesting, and mind-boggling thoughts. Let me show you something which I really believe is going to excite you also enough. Are you able to see this video? Hello? Excuse me. Is this video visible? Is this visible? I think you are mute, Lashna ma'am. Okay, hold on. Is it visible now? Okay. These are the experiments which have been done in the NASA Langley labs earlier to describe the phenomena, which is an aeroelastic instability phenomena known as flutter. We'll see in the second video the formal definitions of flutter quickly, but I would like to show you this video to let you appreciate the power of eigenvalues and eigenvectors and what chaos they can do if we really don't really make them pounded. Yeah. Most of them are the wind tunnel tests of the full scale and little bit on the scale down models in the wind tunnel testing, and later you will see also the full scale models which are experiencing aeroelastic phenomena known as flutter, which is an aeroelastic instability. And it is all happening. Let me also let you draw your attention towards it's all happening to because values really getting excited, which are the natural frequencies of the system because of the forcing frequency from the aerodynamic forces. Yeah. So here what we have seen is the actual testing videos launched and issued by NASA. So let me also ask to excite you again on the topic, which was about to talk about that can eigenvalues collapse a bridge? So let me show you one more very interesting demonstration of flutter. So if you are not able to see the video, please raise your hand, else I will let it play. Is it visible and audible? Pardon me, I don't know why it's happening. Thank you. on the tail of an aeroplane is really vibrating like a spring, elastic spring. It's just happening because of the self-excited oscillation in the aerodynamic and aeroelastic phenomena. And later in the second half of the video, we are going to experience the in the earlier 1940s. So what happened was, what we were seeing was the natural frequencies and the especially the eigenvalues of the structural component were matching with the functional uh, frequencies coming from the forcing function from the right hand side of the equation, which we see that. So that literally led to this catastrophe. I'm just fast forwarding it in the interest of time. On the right hand side of this particular slide, you can see the inset of the three particular parts of the figure, where one of them is the stable region, the second one is the flutter region, the third one is the divergence, which is the fundamental phenomena of instability again. So what we saw is the phenomena which is happening in the middle part of the vibration phenomena in the aeroelastic instability, that is flutter. So this was the whole idea of this particular interaction, which I generally like to interact with the people when I'm in giving lectures physically, is that to have more understandings around that what is the effect and influence of the mathematical modeling in these type of critical systems, which are catastrophic incidents, which we have already seen in the past. So we'll discuss about that, what and which companies are really built on eigenvalues and eigenvectors. But let me begin now with the basics of eigenvalues and eigenvectors, and then we'll go into the other part of the presentation. So in this part, I'm going to talk about that what are eigenvalues, what are eigenvectors, what are complex eigenvalues, the mathematical modeling, and the applications of complex eigenvalues. So let's begin. Eigenvalues and eigenvectors are instrumental to understand electrical circuits, mechanical systems, ecology, and even Google's PageRank algorithm. Most of us are aware about of this particular equation, which is one of the fundamental equation in the matrix algebra, and which we call as eigenvalue problem, or EVP. So Eigenvectors are those vectors whose direction remain unchanged when transformed, especially linear transformation happens via a fixed linear transformation, say T, when eigenvalues are the values where the eigenvalues are the values of the extension factor or the scaling factor. So this is the definition of the eigenvalue problem. But in a geometrical form, to build an intuition around this ax is equal to lambda x, the eigenvalue problem, let me show you this cartoon. So over here, in a 2D system, in a Cartesian plane, let's say we have a vector, a 2 cross 1 vector, so with coordinate x and y represented. So the bold red line over here represents a baseline vector x in this equation, right? In the light left hand side. Now, when it is operated by a matrix A, or it goes under a linear transformation, then what happens if the matrix leads to the vector getting scaled, either scale up or scale down, only scale, no rotation, right? So then that particular vector, in this case x, is known as eigenvector, and the value by which it scales, in this scenario scale up, is known as eigenvalue. Therefore, if you see the vector x earlier, which is a red bold line represented over here, when it is multiplied by matrix x, then it gets scales up by value lambda, and when it becomes lambda x, then the lambda is eigenvalue, and the vector x is the eigenvector. Yeah. So from this equation perspective, our interest is to find only non-trivial solution of eigenvectors x, that is non-zero vectors, using the Cramer's rule, which says that the determinant of the a minus lambda I should be equal to 0. To ensure that, in a mathematical sense, that the matrix a minus lambda I is singular, so its determinant should be 0. This particular equation, determinant of a minus lambda I, is called as characteristic equation, and its roots are the eigenvalues. Definitely, mathematicians know that by the fundamental theorem of algebra, every polynomial of degree n has n solutions in C. Then the degree of characteristic equation will have n number of eigenvalues associated with that system. So this is a little bit of a mathematics. Definitely, all of you, I believe, shall be able to appreciate. But if are there any questions, I'll be happy to address later on. Now let's move forward. Now we have the EVP. Now let's see that how we can obtain the EVP. The fundamental question which always arises in the mind of students, scientists alike, is that, okay, I have understood, appreciated eigenvalues, I have learned about it, but generally, where do I find them? So the second thing which I'm trying to let you appreciate is that the kind of eigenvalue problem we can easily find in the nature. Let me give you an example of a coupled linear differential equation system in a predictor prey model. So here what happens is, let's say x1 is prey and x2 is excuse me, is predator. They both are interdependent on each other, right? Which leads to these two differential equations. So that's why they are coupled, because x1, rate of change of x1 is dependent on excuse me, x2, and indeed x2, the growth rate, is dependent on x1. That's why they are coupled, and they are definitely linear differential equations because their degree is 1, and they represents the differential equations over here, especially ordinary differential equations. Excuse me. Notice that system of differential equations can arise quite easily from naturally occurring situations, and I have no doubt to say that most of us are, might be modeling using data science or many other domains at their home or doing this quarantine as well as during these other time, the pandemic model, which is the SIR, one of the famous model, the susceptible, infected, and recovered model, is also the coupled differential equation model, although they are not linear. So note here we can write nth order linear differential equation as a system, and the idea is to convert that coupled differential equation over here into the matrix form, so that we can enter from the algebra to the matrix which we really want to deal with, so that we can get the eigenvalues out of it. So the above equation, the coupled set, we can write that into this matrix form, that is x dash is equal to ax, where a is the matrix which we can form by the coefficients of these coupled differential equations. Now here, the eigenvalues of matrix A will be complex. We want to see them, then what happens? We know that the equation is of the form of a pure exponential. In this scenario, when we have x dash is equal to ax, then we obtain, when we put that values into this equation, we get our eigenvalue problem where we started with. And so the objective, as I said earlier, the objective is to find the determinant of a minus lambda ix should be equal to 0 to really find the lambdas. And from matrix algebra perspective, to let the appreciation from a matrix algebra as well, we can say that the vector, the eigenvector x, is in the null space of a minus lambda I, and the eigenvalues lambda is chosen such that a minus lambda I has a null space. So I really don't want to detach the intricacies and the appreciation of the matrix algebra, but at the same time, I will also would like to give an equal weight to the whole fundamental phenomena of applied mathematics and applied science and their knit. That's why I also want to highlight over there that this is really one of the key things which has been developed, and the whole credit goes to the people who did the matrix algebra evaluations earlier. So to be of use, so we want to ensure that the matrix A minus lambda I is singular, that is the determinant is equal to 0. So now here is the key thing, where the question which, with a small anecdote where I started, that what is the physical inference if you really want to understand that the eigenvalue lambda is a complex number. So now focus, please, I would like to draw your attention towards this. Now focus on the response x of t for larger times t. Since eigenvalue is a complex number, so we can represent it as a real part of lambda and imaginary part of lambda. Let's say lambda is equal to alpha plus iota beta. Then equation response or system response will be determined unstable if it approaches infinity, or if we say the lambda value, the real part of lambda, that is alpha, is greater than 0, then you can see that if you put it over here, then the exponential will really blows up. It is neutrally stable if alpha is 0, and it's stable if the, sorry, I think the real part of lambda is less than 0, then the exponential will decay. And however, the complex part of the eigenvalue, that is beta, leads to oscillations, because e raised to power iota beta, if I put alpha e raised to power alpha plus iota beta is equal to, then e raised to power iota beta t is a representation of, we can use the identity e raised to power iota theta is equal to cos theta plus iota theta. And here the decay or growth is governed by e raised to power alpha t. Let's see by an example, whatever we have discussed over in the last two slides. Let's quickly understand by a quick example. Then I would like to relate that with the physical inference. Let's take that predictor frame model again here, which earlier we modeled in the matrix equation, that is x dash is equal to ax. And with an initial condition that x0, it becomes the EIVP, initial value problem. The eigenvalues and the eigenvectors of this matrix we can calculate. So I am also giving you the solution, so you can really do this exercise later on, but in the interest of time, I'll quickly go through this. So the determinant we'll find, and here, because it's the 2 by 2 matrix, we'll get the polynomial, which is the characteristic equation, and equate it to 0, and we'll try to find it. It's a quadratic because it's a 2 by 2 matrix, as I said earlier, because of the fundamental theorem of algebra. Then we find the two roots of this equation. These are the eigenvalues, lambda 1 and lambda 2, and they are conjugate pairs because they're complex number over here. And now the eigenvector for the first eigenvalue, let's say lambda 1 is 2 plus 8i, we need to solve this particular equation, right? So when I put lambda over here, then these are my eigenvectors. If I really put it over here, then the first eigenvector is this. Now, the solution corresponding for the found eigenvalue and eigenvector, we can club it. The general solution, because it's a linear differential equation, the principle of superposition holds true here, and we can write the solution as the addition over here because of the observed two eigenvectors and the associated two eigenvalues. Now, if we apply the initial conditions to find these constants C1 and C2, we can easily find that their values from the initial conditions from our IVP, initial value problem. Now, then so we started with the equation for the predictor equation, which is a set of linear equations, linear differential equations rather. And then we formed an EVP, eigenvalue problem. We solved that eigenvalue problem, found that the eigenvalues are the complex eigenvalues. And then we found its eigenvectors, associated eigenvectors. Using superposition, we constructed this particular actual solution. So the eigenvalue is written over here, and here in the left side, you see this particular plot. This is known as phase portrait of this dynamical system. So phase portraits is a representation of the dynamical system, which tells us about the stability of the system, the dynamical response stability. So here we plot the two x1 and x2 responses of the system together to see that whether the system will be stable, neutrally stable, or unstable. And these, as I said earlier, so this is the crux of that. If somebody asks you that what is the physical interpretation of a complex eigenvalue, or rather an eigenvalue in general, then this is the whole summary, which you should really definitely a takeaway message, that if the real part of the eigenvalue lambda or alpha is greater than 0, then the solution will be unstable. In this scenario, this is unstable because the solution is really blowing up. It can be neutrally stable if alpha is 0, stable or asymptotically stable if alpha is less than 0. And if you see the response, which we'll see that in a live demonstration very soon, that beta, the imaginary part of the complex eigenvalue, represents the oscillations which happens in the dynamical system. So this slide is the most important take-home slide. Yeah. Let's quickly get into the applications of eigenvalues. So here I have listed some of the applications of eigenvalues. As you see that the eigenvalues are used extensively in aerospace, mechanical sciences, applied mathematics, civil engineering, ECE and electrical engineering, artificial intelligence, machine learning, quantum mechanics, and of course, this is one of my favorite. Some industries are also built on eigenvalues and eigenvectors. And one of the biggest industries which touches all of us indirectly or directly is Google, and it is built on eigenvectors, only eigenvectors in late 90s. When paper came out by Sergey Brin as a research project in Stanford. Let me quickly go through that when I say that it is quite highly used in these particular fields which I have listed earlier. So eigenvalues are used in designing bridges. The demonstration of that, we saw that in the motivation slide. So the natural frequency of the bridge is the eigenvalue of smallest magnitude, which has the maximum energy in the eigenmode that models the bridge. So engineers, especially civil engineers, for designing bridges, exploit this knowledge to ensure the stability of the constructions. In communication systems, especially for ECE students and EE, uh, you all will be able to appreciate Shannon because of Shannon theorems and the lot of contributions by Shannon. So eigenvalues were used by Shannon to determine the theoretical limit to show how much information can be transmitted using mediums like telephone or through the air. In structural dynamics, aerodynamics, or mechanical sciences in general, eigenvalues are extensively used for structural dynamics, modal analysis, dynamical stability of structures, dynamic buckling, CFD, computational fluid dynamics, and computational structural dynamics interactions, which is also known as FSI, fluid structure interactions, finite element analysis, etc. As many of you will be already quite equipped with the subject of machine learning because of the courses you're going through in your curriculums, and the industry is also galloping. So it is extensively used. Eigenvalues are also used in machine learning and AI. One of the key contributions is using PCA, that is principal component analysis, which is used for dimensional reduction of big data or large data sets, which also increases the interpretability, but at the same time, minimizing information loss. It does so by creating uncorrelated variables and successively maximizing the variance. So it essentially finds the principal components by reducing to solve and the eigenvalues and the principal eigenvectors associated with that. Eigenvalues and eigenvectors are extensively used in quantum mechanics, which is also touching and influencing quantum computing, which is also one of the key fundamental and galloping area of research in the today's era. So the Schrodinger equation for the harmonic wave oscillator have Schrodinger wave functions, which are also eigenfunctions. So let me show you quickly the demonstrations, which I promised you earlier, by visual mathematics. So what we have shown and discussed earlier was the appreciation of the subject of eigenvalues, especially complex eigenvalues, by its applications and the catastrophe it can do if we really don't put a due attention to it. Second, we saw that whatever we have, how we divide and extract the fundamental mathematical models from the physical systems and then draw the eigenvalue problem, how we solve that eigenvalue problem, get its response, and plot its phase portraits. And then we saw its applications in the standard areas of engineering and the like. Now, let me quickly go to the demonstration. And for that, I'll be switching my screen and to go to the Mathematica. So are you able to see my screen? Yeah? Okay, thank you. So here you can see one of the phase portrait plots. These are basically known as flow maps, also in nonlinear dynamics or modeling and simulation courses. So over here, if you see that earlier, we discussed about one fundamental equation, that is x dash is equal to ax, right? So over here, where my mouse is hovering, I'm actually showing you that on D, where I have actually exploded A by its 2x2 matrix entries, A11, A12, A21, and A22. And yes, x1 and x2 are the responses of those coupled linear differential equations. which can arise from all these kind of subjects, which you saw that in the third part of the presentation, from any of the application areas. It can be aerospace and the like, right? So now here, this is really something which I always wanted to really show and discuss with the students, and I always wanted to learn in this way, but I learned it later on, and that was my motivation to share it with you all. So here you can see that this is the visual part of the mathematics, which is a subject really coming along today globally. So here what we can do is we can really manipulate these entries rather than actually in a MATLAB or in any kind of a system equivalent like Python these days. People try to really keep, put these matrices and then plot it using the libraries in build or external. But here using Mathematica, you can do that in a really demonstrated way. So if I really increase the number of any of the entry associated, then I actually indeed are updating this particular equation. And what I'm updating is deliberately I'm updating one of the entry at a time. And by doing so, you can see over here, the flow map changes. And if I have to say, so here in these flow maps, so you see the x1 and x2 both are plotted, then how their response is changing, right? And in the left-hand side, you can see the corresponding eigenvalues, where the horizontal line represents the RE represents the real part of the eigenvalue, remember, which is alpha. And on the vertical line, it represents imaginary part, represented by IM, imaginary part of the eigenvalue lambda, and that was beta, right? You can please refer to the presentation, which shall be shared by the organizers. So as I change the entry, please observe, I change this matrix, I change this value, I change this matrix, then the eigenvalues also change. Please see, right? This is so sensitive. That's why eigenvalues are very critical to understand deeply. If we really mess up with the understanding of eigenvalues, and especially complex eigenvalues, which generally happens and are observed in all the natural phenomena, especially in buildings. If any one of you are have visited Dubai, you have seen these skyscrapers over there. They all go through rigorous testing, and the knowledge of civil engineering is really at a stake. And they all are really masters of this particular fundamental of complex eigenvalues, because this is what is actually happening in the background of life. Mathematics is always at the play, right? Let me show you one more thing. You can play with this. I can share these codes if any one of you like on my LinkedIn or GitHub page. And then if anybody you would like to see that, then I will share that with you. But let me show you one more thing, as I promised. Now here you see, earlier we saw the phase portraits, which represents the stability of the system, which is critical from the nonlinear dynamics perspective. But we live in a system that we would like to see what is the system response with respect to time. Tell me, please. So here is the solution. So now on the x-axis is the time. On the y-axis is y1 and y2, which are the response of the two vectors. And again, if you see, I have the entries of that equation. X dash is equal to ax, where A is a matrix, a 2 by 2 matrix, and its 2 by 2 entries are written over here, A11, A12, A21, and A22. And as I change, please look at it carefully. As I little bit perturb any of the values, the system can be stable. If I change it a little bit, system can really go into explosion. Please see the values over here, 10 raised to power 9, right? So similarly, you can look into these understandings yourself to see that what is the criticality of eigenvalues, and especially complex eigenvalues, and what are its importance in our day-to-day life. All right, I'm switching to the slide. Okay, how much time I have? I think I'm on time. It's going to be 5. So in the interest of time, so I'm closing my presentation with these two particular questions which I have asked to the audience. I'll give the answers to that, but if anybody of you would like to further explore and would like to discuss with me, you're more than welcome for that. Okay, can you tell, as I asked you, the famous algorithm which utilizes eigenvectors and which revolutionized the World Wide Web? The answer is PageRank algorithm. And the paper, which was a seminal paper, which really founded Google, which is our lifeline of today, and definitely which is part of the Alphabet parent company. And it came out as a research article from Sergey Brin and Larry Page. You can look into that. Second question, and the last question was, can you tell me the worth of eigenvectors? In 2004, for Google, it was $1.9 billion. In 2004, when it was listed, its IPO was listed first time. So in 2004, remember, so I'll end my presentation as I promised to respect the time. It's 4:59, and I'll leave you with its thought and the takeaway message already sent you in the slides. And with this particular comment, make complex easy, please. That's the responsibility of all engineers and scientists alike. And thank you for giving me this opportunity. And all of you are encouraged to interact with me and in any of the, and give me the feedback to further improve and also share your thoughts and collaborate. Thank you all. Not able to listen to you.
Am I audible?
Yes, yes, please.
Yeah, thank you very much again. It was really a wonderful talk. Even I was lost at your screen, and so it was really wonderful.